Good afternoon, everyone. My name is Gwendal Grignou, and I'm here to talk to you about the sensor. I'm the tech lead in the Chrome OS platform team on sensors. So let's go to the slide deck. Okay. So before we go dive into the gory detail, I want to talk about what I mean by sensor in Chrome OS. So the sensor I'm going to talk about today is what we call the MEM sensor, the mechanical anyway. So the mechanical electric anyway. So the MEM sensor, the small sensor like the gyroscope, accelerometer, compass, light sensor, proximity sensor. So why I'm limited to those sensors is those sensors are managed in the Linux kernel by the IIO subsystem. IIO stands for industrial I/O. So I'm not going to talk about other sensors like input device, mouse, keyboard, or fan control or temperature sensor, which are managed by other subsystems. So now we can go in more detail, and I'm gonna give you overall presentation of what today we have implemented in Chrome OS. So traditionally the sensors are connected to not connected directly to the host, what we call the AP, the application processor, but are connected to sensor hub, or what we call here embedded controller. We could have several embedded controllers per device, but generally we only have one embedded controller on the sensor are connected to it. Why we are doing that is the EC, embedded controller, is very power efficient and it runs all the time. So for example, if you have the Pixel C here, and even when the Pixel C is off, we can press on the back of the Pixel C, and the light bar will show the power usage. So in this, what happened on this device is the accelerometer is on, the EC is on, and when the accelerometer indicates there is a double tap, it wakes up no, it doesn't wake up anything. It's light on the light bar with the power. So that's why we connect the EC, the accelerometer to the EC, so that the EC in the low power domain is doing the work of collecting information. Then when the EC has information, when the AP is on, it will send it to the kernel. So that's the green box here. So there is a transport layer via SPI, SQRC, LPC, and then it will go to the sensor stack, cross-EC sensor, and then for this kernel module will differentiate the different events depending on which sensor, and then those events will be collected by application. So in the current implementation, there is actually two class of application. There is Android, which has full control of the sensor and can run them at high speed, and for application like games, and everybody else, which are poking at the sensor using a different path, like Chrome. So why Chrome is poking at sensor? So if you have an example here of a laptop, so most of the Chromebook are convertible. So when you put them into tablet mode, we use the two accelerometers, one in the lead and one in the base, to calculate the lead angle. And then we can rotate the screen. We can rotate the screen when it's depending on the orientation of the sensor. So that's why Chrome. Actually, that's the main usage of the sensor in Chrome OS today. The games, yeah, there is some games, but yeah, it's on a big device. It's not that good. Anyway, so we also have the that's not true. There is also the light sensor to when you do auto dimming on the display. So That's the current implementation. There's several problems with this implementation. So the big one is when I work on it like 4 years ago, I introduced a driver like cross-CC sensor ring, which is not upstreamable because it's not exactly it's not a driver for a particular sensor. It's just a driver that collects all the sensor information and send it to Android. So this is not upstreamable, and moreover, it doesn't work with VMs. So that's why we are working very hard to change this current implementation and make it better. So as I said, not streamable, doesn't work with the VM, any VM actually, not just the RVM, and it's also inefficient for other applications. They have to poke, they have to gather the data from the sensor. The data is not flowing to the application. So what Hervé is working very hard is to introduce a service. So I don't know if you saw so many presentations those days, but Chrome is all about servicification, and IO service is one of those services. So the idea is we collect the information from the kernel using an open source library called lib.io, and then we spread those events to whoever asks for it. And there is no, everybody have the same access to sensor. So lib.io project which is the main, the architect is the same person that wrote the IIO library in the kernel, as a network conduit. But for us, it was for Chrome OS, it didn't work out, and we tried to fit it in, but we came back to Mojo, which is widely used in Chrome, and it works pretty well, and it's easy to get working example. So we decided to create a Mojo interface, which is very similar to what the IIO interface will offer, so that make it possible to support any kind of sensor. So every application will register itself to the IIO service on the traditional way of Mojo, and then the IIO service, when there is sample, will call will send a Mojo packet, and I will wake up the particular thread. So with that, we could have many more applications using the same sensor, which is important. The way the kernel has been designed is only one person can use a sensor at a time. So you will have Chrome, as seen before. We can have the camera if we want to do image stabilization, the camera stack. We can have PowerD that also using the sensor. So for instance, if you're stationary on a desk, but you have several Wi-Fi access points, it doesn't make sense to switch access points. So we could be smart and say, oh, I'm stationary, the access point come and goes, no need to move. So that's one application for a sensor. On the usual, we can use also the Mojo interface to connect to RPM. And one benefit is as I said earlier, flex to sensor. So until it's still in demo mode. So, but I took a screenshot. With this service, we will be able to access the web application. We'll be able to access sensors using the web API generic sensor. And there's a website which demos some application, and we can gather data. Another advantage is the IIO service right now connect to the cross-CC stack, sensor stack, but given it's a kernel interface which is well described, could connect to other IIO-based stack pretty easily. So one standard in the Windows world for supporting sensor, it's called the HID stack, Human Interface Device. And there is some extension for the sensor. So there is some drivers. So technically we could, maybe until it's tested, it doesn't work, but it should be pretty easy to use. Potentially, we could use the Android context hub yeah, I forgot this one. The CHRE is the what is used in Android phone, like the sensor hub for Android phone is based on CHRE. So there's more work there, but same idea. We event flow to IO service and we spread them. And we can also implement new features. So in the EC, we try to use the EC with as little RAM and flash as possible. So some feature which are traditionally in sensor hub on phones may not fit on the EC. So I'm talking, for example, of composite sensors where we have sensors which are a mix of other sensors. Like, for example, we can merge magnetometer, accelerometer, and gyroscope in a sensor to do a dead reckoning to know where you're moving into a room and through what we call a Kalman filter. So we could have those sensors. When it's not in, today we let Android implement it, but Android has signaled that we should implement it outside of Android. So that's where we can put it in the IO service. The support also the sensor which are normally when you get sensor information, we add automatically the calibration, but some application may want to do the calibration themselves. So we could also report uncalibrated sensors. So the same sensor can be described as two different sensors, one with calibrated and one with uncalibrated information. So that's the idea of IO service. Something I mentioned in the slide is the IRQ filtering, move to user space. So what do I mean by that? Is something we noticed when we work on the sensor stack is when I first worked on the Pixel C like 4 years ago, the requirements for timestamping were not that tight, and we took some freedom with it, and we implemented some embedded controller without the hard IRQ from the EC to the AP, but using a soft IRQ via CPI, and that introduced some variation in the latency. And even with the hardwire IRQ between the EC and the AP, there is some noise. So I took a sample on a machine with a hard IRQ, and even there, you could see the red line. You could see quite a lot of noise. The sensor is working at 200 Hz. So I moved the red line by 2 milliseconds just for visibility. So you see that there is some noise. And this noise is not due by the sensor. The sensor is pretty reliable. I send an event every 5 milliseconds. The EC has a very low latency too, but it's the time for the host to get the IRQ, to wake up the sensor stack, and the sensor stack for retrieve the information. This delta here, there is variation in the timing. By using a median filter, we can narrow down the timing to be much more acceptable, much more center around the 5 millisecond mark. So that's a median filter. It's there's a little bit of math there, so it doesn't feel right to be in the kernel. And those features can move to user space. That's the subject of the next slide. Is when we add new feature, we could do it. We could add the code at 3 different places: the embedded controller, the kernel, or the service, the IO service in user space. So adding in embedded controller is nice. if for new feature that will only be deployed for new device, if it's a bug we have to fix, if it's a feature we have to install on older device, it's a little bit more difficult to deploy because we have to do some firmware qualification and it takes time, and there's less will to do that on the device that already shipped. So when we have new feature, having it in the EC is not great. For instance, when I talked before about the need for the filter, and it happened that when we upgrade ARC from N to P, and there was new requirement for the sensor timing, and then it was very, very painful because we had to backport a lot of change in older machines to fix bugs and make the timing tighter. So yeah, that was pretty difficult. The kernel is also it's slightly easier in the kernel, but still we have to backport we have to upstream first. That's the Chrome OS policy. We have to upstream first and then backport to all the kernel we support. So that's extra work here. The main problem with the kernel is the testing. I mean, it's a little bit difficult to test a new feature, like for example the filter. It's possible, but it's a little bit more difficult to mock compared to the EC or IO service. But where the EC shine is when it's in terms of power consumption. When you have sensor at full speed, only talking to the EC and EC is processing its data, there is the EC power consumption is in milliwatts. When we have to wake up the host processor, the AP, that's much more power intensive, and that prevents the host going into S0IX. So that's not good. But it depends on the application. So that's lead to the event-based sensor. So in the old time, so I show the machine here. In the old time, to calculate the lead angle, the Chrome will query the accelerometers from the base on the lead every 10 milliseconds. So every 10 milliseconds, even your computer sits on the desk, every 10 milliseconds will gather the event. And we actually calculate that on some platform that can consume up to 2% of the CPU time while we are idle. So we have the EC, or actually other sensors, they have the concept of event-based sensor where you are not interested in the data by itself, but you're interested by events. And in the case of the lead angle, you don't care about what's your angle, if it's 90 degrees, 187 degrees, or 270 degrees. What you care is, do I go beyond the 180-degree threshold where I need to move in tablet mode? So that's where the EC has defined an input device where you have where it will send a pseudo key called software tablet mode to move to indicate that we are either in clamshell or in tablet mode. There is also the IO sensor. The IO framework also supports event-based. So what you will do is, instead of listening of event to a well-known device path, you will send an IOCTL to a device file, and it will tell you on which file descriptor to listen to, and on that particular file descriptor, you will get event. So one particular sensor which uses this feature is called the SAR sensor. SAR, if I get it right, stands for signal absorption rate. So it doesn't measure the signal absorption rate, but it's a sensor which we are required by the FCC to prevent giving cancer to people by requiring the FCC require that when you have a human nearby an antenna, either it's the LTE or the VLAN, the wireless, the Wi-Fi, we need to power the lower the power of the antenna to prevent harmful radio emission. So what the SAR sensor is made of? So you have the SAR sensor itself, which basically is a converter between capacitance and voltage. So it will measure the capacitance between two conductors. So the antenna here is just copper, and when it detects a change in capacitance, it will send an event it will raise an interrupt, and then it will send the driver will query the sensor over the I2C bus to find that there is an object is near or far. So it's actually not trivial. The antenna design has to be done in such a way that when you approach the end, then over the antenna, we lower the power before that we are actually on the antenna itself. Also, we have to make a difference between someone holding the power or the tablet on a table, which also change the capacitance. So that's where we have the SAR sensor. But after configuration, after initialization, when we are not debugging, we are waiting for events. So SAR sensor, we are putting it on the devices when required. So it's expensive and it's not straightforward. So we have been looking at another design which exists already on other machines. Annabelle and Shinkan have been working on a design where we use the accelerometer to do on-body, off-body detection. Basically, is when you hold a tablet, you're vibrating. And we can measure this vibration with the accelerometer. And when we feel there is a vibration, so it's basically a low-pass filter. We calculate a coefficient and we think vibrating. We are on-body. And we don't, once again, we don't care about the exact measurement. We just send an event. We detect a body, and then when you drop by the device on the table, and we have a long time. We have a 15 seconds of no motion. Then we will go back to the off-body mode. So the beauty of this algorithm, it's free because we already have the accelerometer, already pay for it, and it's pretty efficient. So it could be used for lowering the power to the Wi-Fi antenna. Yeah, another usage on some Windows machine that's way it has been used is when you hold your laptop on your lap, we can lower the CPU power, the CPU frequency, so that especially on fanless device will not burn your legs. Our legs will not be burned when we are using intensively the Chromebook. So that's another usage of this on-body, off-body virtual sensor. So a little bit more forward-looking, I want to talk about something very exciting we are working on, which is called SOLI. So SOLI, I mean, there's already presentation on the web. It's already on the latest Pixel phone. It's also in the Nest product, and it's a completely new kind of sensor where it's a radar in a 50 gigahertz band, which measure the collect information, and then you have a processor to make sense of the information, and then some information to the host. So what SOLI can do is gesture recognition, like swap, and we call large gesture recognition. We can do also tuning, like routing like this. We can also do presence detection. So it will be able to detect, to see if there is a face in front of the computer. It will be able to detect if there are several faces in front of the computer. It will not be able to detect who is looking. It's not that precise. Which is actually good for privacy. But yeah, so we can, one potential usage is when you stand up from your desk, the machine automatically locks. When you sit on your desk, before you do anything, the machine resume and present the logging screen. It will not be able, you won't be able to do a Face ID or stuff like that, but at least you can present the logging screen. And you could also, when you have multiple users, so guess that people are watching movie, or then you don't go in sleep. You change the sleep timer. And we could think about other applications like but yeah, that's the idea. So presence detection. So how does it work? Is so here on the slide deck you have the PCB size of the device. It's very small. You have the SOLI, the radar itself, and then the corner you have the signal processor, and then you have some flash. That makes a standalone device. So it's a standalone device. When you are when you're just interested in SOLI events like gesture recognition, you use very little bandwidth. So right now the DSP uses UART connected to the host, and UART is listening to the serial. It's a serial port, and the application is listening to the serial port, and then if you are in the learning mode, then you use a different interface and much more bandwidth, and then you collect information from raw information from the SOLI itself. You have a control application, and then you have a different application to process that data and infer, calculate a new inference engine you will put back into the DSP. So yeah, so that's very exciting. Like Emre is working on it, setting up demos, on making changes. It's completely different world from the what I've been working on, where I deal with the I2C drivers and moving message back and forth. Here, it's the main. I mean, I would say the one big challenge is the machine learning, where for example, right now we have SOLI working on a Pixel phone, and the distance to enter to wake up the device or to lock it it's around 1 meter, but for a Chromebook doesn't make sense. Your sit usually further away. So changing the parameter is just not going to the code and changing a constant and then recompiling. You have to retrain the SOLI, you have to gather data, and then with that data, you can flash back the new inference engine. So that's what I want to say. Like something which is pretty new is the machine learning coming into Sensor. So I talk about SOLI. Low resolution camera, if we want to use it, has also the same interesting feature. And there is also if you look at the datasheet for the latest accelerometer of Jaro, there is also some vendors are promoting machine learning inside the AMU, inside the sensor itself. So that way you train the sensor, you gather data, and then you write some macro code, and then the macro code will automatically has been trained to trigger when certain gestures have been observed. So it's a teeny machine learning. I mean, it's a very teeny it's a very teeny part of the sensor is doing this processing. And we could argue, for example, in the on body, off body, or for example, we have also the pickup gesture. You don't need to have machine learning for that. You can do it with the regular filters. But I mean, more complex gesture, we can think of using machine learning as well. So yeah, so that's conclude my talk, and I'm gonna look at Slido for the questions. And yes. So when can we use fingerprints of face recognition Chromebooks? That's a good question. So fingerprints, the fingerprint is do exist actually. If you have Asus Flip here, you have a fingerprint sensor here. So fingerprint is a different interface than IIO, and it's usually connected. It has its own embedded controller for security reasons, and it's connected. Usually, it's connected to the host via serial port, so it's different. But yeah, I think the main limitation for fingerprint is cost. The technology is there. It's just it's on the mid-tier high-end. It makes sense. We're already working on fingerprint sensor. Low end, it doesn't make sense too much. Fast recognition is that's also the same thing. I mean, you obviously don't want to do face recognition with the full camera for privacy reasons, so you need extra sensors. That also is cost money. So yeah, so that's different from what I'm working on. But yeah, fast recognition is could potentially be there for mid-tier high-end device. But it's once again it's a cost issue. Okay, thank you for the question, and I hope you learned something today. And it was a pleasure to give this presentation. Bye bye.